All right, here's warm-up number 11. If Ed is a third grader, then he is in elementary school. Okay, if possible, I'm supposed to write a true biconditional. So a biconditional is an if and only if statement. So if this works, it would say something like Ed is a third grader if and only if he is in elementary school. So now I could write that and it would be a biconditional, but in order for it to be a true biconditional, I need two things to happen. I need the original to be the original conditional to be true, and then I need the converse to be true. So let's look at this original. If Ed is a third grader, then he's in elementary school. To me, that sounds true, right? The third grade is in elementary school. Okay, so that part we're good on. But if we look at the converse, I'm not going to write it out, but let's just think what it would be. So the converse, I would flip this around, right? So it'd say if Ed is in elementary school, then he is a third grader. Well, if he's in elementary school, maybe he's a third grader, but maybe he's a first or second or fourth or fifth grader, right? So that's not necessarily true. So the converse here is false. Both of these things have to be true in order to write a true biconditional. So I'm going to say, if not possible, explain. So I'll say not possible. And then my explanation, you can say just the converse is false. That would be fine. Or you could give a reason why the converse is false. You could say if Ed is in elementary school, he might be a second grader as a counterexample. I'm just going to say the converse is false. Okay. All right. Next up, we've got this is a geometric proof actually, because we've got some geometry happening here. We have two line segments, and we're gonna remember when we have two line segments, you can add them up to get the bigger line segment. That's the segment addition postulate. So that's going to come into play here. Okay, but let's start breaking this down. First, I'm looking at this statement. I'm supposed to fill in the reason for this. Why is this true? Well, this is true because it's given. We're just told that it's true, right? It's given in the diagram, and also up here it's just written as given. So that's always going to be my first reason, given, okay? And then from there on out, I'm going to have to think a little harder to figure out what my reasons are. So let's look at step B. This says KL plus LM is going to be congruent to KM. I guess I should really have marked those as segments, but okay, so this segment plus this segment equals the whole thing. Well, I was just talking about that a minute ago. When you have two segments joined together, they form a bigger segment. That's the segment addition postulate. Usually I abbreviate, so that's fine if you abbreviated there. Okay, so next, so we have this equation. Now we've got a new equation, but now it's not the names of the segments anymore. So now instead of KL, I have 2x minus 5. Well, if we look in the diagram, 2x minus 5 is an expression that represents the length of KL, right? And up here they tell me KL equals 2x minus 5. So what I can do, I can substitute in 2x minus 5 for KL, right? And likewise, I can substitute in 2x for the length of segment LM, right? And same thing with KM and 35. So I've substituted. This is the substitution property. And you can abbreviate, but if you just put sub, I might think you meant subtraction. So make sure you get far enough so it's clear it's substitution, okay? And then looking at this, well, now we've just got an algebraic equation, okay? And if you combine the two x's, then you get 4x, which is what I have here, okay? Now, a lot of times I'll see people say, oh, I added those together. This is the addition property of equality. But no, it's not, because you're not adding anything to the right side of the equation. Remember, addition property of equality, or subtraction or multiplication or division, you'd be doing the same thing to both sides of the equation. Here we're only working on the left side of the equation and combining these, okay? So you can call this simplify, and it doesn't matter which of these reasons you give, because they both work. Or you could say, hey, I combined like terms. These are like terms that I combined. Either one of those will work. I kind of like combined like terms because it's a little bit more descriptive of what's happening, but either one is fine, okay? And then let's see, now we're at step D, okay? So how can we get here? Well, you'd add 5 to both sides, right? I don't care if you write the little +5 on both sides, but I'm just trying to illustrate how we get from this step to that step. We're adding the same thing to both sides, so this is the addition property of equality. I'm abbreviating there a bit, okay? And then the last step, let's see, we went from 4x to x and 40 to 10. Well, you can achieve that by dividing the whole equation by 4. So this would be the division property of equality. Okay, and then we've got all of our reasons. And there's a 2-column proof. Okay. All right, see you next time.